Hi, I'm ChristinaWan, a Grow intern at BU's physics department. I'm studying ion bombardment and its effects on stress evolution. As thin film and semiconductor industries have developed and manufacturing has been occurring on an increasingly small scale, the need for nanoscale surface processing has risen. Exposing surfaces to ion radiation has been prevalent in manufacturing, making it a less costly technique that can replace direct write methods for surface shaping and cleaning. As ion-induced stress influences the rearrangement of atoms in thin film properties, understanding the conditions for stress values is essential for understanding the nanoscale topography evolution. To measure stress, we measure the curvature of a silicon sample and use Stoney's equation to convert it into stress. To determine the wafer curvature, we use a multi-beam optical stress sensor system that shoots a laser through two etalons, splitting the laser into parallel beams and then forming laser dots on the silicon wafer, which is then reflected into a CCD, a charge-coupled device, and where the spacings between dots are recorded, and then the mean differential spacing, which is the average of the change in all spacings, is then converted into curvature via the inverse radius equation. We conducted experiments with incidence angles ranging from 0 to 75 degrees, and we find that there is a compressive spike during the beginning of ion bombardment, which is predicted by the Swenson's model and observed in Joy Perkinson's experiments. We also find that the peak decreases in magnitude with increasing incidence angle. And finally, we also find that in samples that are smoothened previously by normal incidence, the compressive spike is much smaller and brief, and there is a tensile stress that follows, which is not predicted before. And the potential applications of these include those in solar panels, band gap engineering, and biomedical fields.